As we've developed solar telescopes, our view of the sun has changed dramatically, especially since the space age. We can now send telescopes into space and observe the sun using X-rays or ultraviolet light. And the detail that these send back is incredible. One example is the recent Solar Dynamics Observatory, which is really very much like a Hubble for the sun. That sun that we see with this instrument is rapidly changing. It's got all sorts of structure, and it's very violent. Now, to give a sense of the scales involved in the solar system, okay, I have an orange here. No prizes for guessing what it's going to represent. Okay, if you were to take the sun and reduce it to the size of an orange, scaling the solar system accordingly, the Earth would fit into this model as a grain of sand, about 8 meters away, which I reckon is kind of where the row of seats back there meets where the tables begin. We live on a very tiny part of the solar system itself, a very tiny part of the galaxy. And I could go on. And this sun, well, the sun is a nuclear reactor. So powered by nuclear reactions, its atmosphere heats up, so that its outer layer, the corona we call it, is 1,000,000 degrees Celsius. And this hot gas, it starts to blow away from the sun because of this heat. We call that the solar wind. The sun loses 1 billion tons, it's 1 billion kilograms, 1,000,000 tons of material every single second in this way. And that material flows out from the sun, heading towards the edge of the solar system. On the way, it breaks the sound barrier, and it comes past the Earth at supersonic speeds. Its properties change, depending on what part of the sun the solar wind that we're receiving is coming from. If you measure a solar wind at 400 kilometers per second going past the Earth, well, we call that a slow solar wind, because there's an even faster one, which is 750 kilometers per second. Well, in astrophysics, you measure something at 400 kilometers per second and call it slow. Now, this material, as it comes past the Earth, it begins to interact with the Earth's magnetic field. It's very tenuous. If you took a cubic centimeter of air in this room for comparison, so something about the same size as a sugar cube, that would contain 10 billion particles. Okay, if you wanted to count up to that number, you would need more time than there is time in the universe so far. Take that same volume up into a solar wind, the number of particles it contains is 10. So that's why we think of space as being an excellent vacuum. But those particles still do interact with things, especially when magnetic field's involved. Now, that solar wind, when it comes past the Earth, it begins to stir up our magnetic field. And to use, again, an example in the room, an example of what happens when you stir up a magnetic field, well, I have here a kind of hand-powered torch. It has a magnet inside it and a conductor from a wire. And I can kind of stir things up by using things, and I produce electricity, which in this case generates a light. When the solar wind interacts with Earth's magnetic field, it again produces electricity, it creates voltages, and that starts to drive particles down into our atmosphere. And when they collide with the very top of our atmosphere at those high altitudes, that's when you see auroras. Now, in terms of predicting good auroras, a couple of things that help. One is that the solar wind is coming fast, then there's more energy. Things are being stirred up more quickly, you tend to get stronger voltages. That's something that we can predict. Another very key thing, though, is that solar wind also contains a magnetic field. And if that magnetic field is in the same direction as Earth's, it kind of spins around as the wind comes on its way to us. When it's pointing the same way as our one, the Earth's magnetic field is actually very well shielded. It can repel this new magnetic field. And then the auroras tend to be weak and faint, and that's to people in northern Scandinavia. If it turns the other way, so it's in the opposite direction, then conditions improve. And the auroras become much brighter, and they start to head south a little bit. So the people up in Inverness, they may be starting to get a chance at this point. But it's not quite good enough for us down here in Dundee. To send auroras this far south, we need something really a little bit special. And that is a solar flare and a coronal mass ejection.